Hello. Continuing from yesterday's thread, we are going to deep a little bit deeper on Josephus problem. We had a recursive solution on even number and odd number input. This time we're going to generalize a bit whether there's a different trend we can find out from uh, with the input of the Josephus problem. So here we have the input n to 16, and we can group by, we can look at the pattern that it kind of uh, repeats a circle looking like where when n equal 1 is 1, but from 2 to 3 it's back to 1 and now increased by 2, which is 3, and 1 2 3 5 7, and another from 8 to 15 and input it becomes again 1 3 5 7 9 11 8 13 15. So it looks like they are grouped by 2 to the power of n, starting from 0 1 2 3, and they are repeating in odd numbers. How far it goes is it's like 2 to the power of n. So what we mean by that is Jn is always 1 at the beginning of a group, and it increases by 2 within a group. So if you write n in the form, here I'm just gonna reread what the text says. So if you write n in the form n equal 2 to the power of m plus l, where 2 to the power of m is the largest power of 2, not exceeding n, and where L is what's left, the solution to our recurrence seems to be J 2 to the power of m plus L equal to 2L plus 1. If it seems a little vague to you, let me write an example here. For example, we have J6. If you organize this 6 into 2 to the power of what's left over fashion, it's going to be 2 to the power of 2 plus 2, right? Now, 2 is the L, and again, M is also 2. It's going to be 2 times what's left over, which is 2, plus 1. So the Josephus for input 6 is 5. As it should be from our table above in this case. So this is kind of there are two catches, two things you need to catch is that the limitation of what 2 to the power of m should be is that it should not be exceeding n, and L is the leftover. So if you have the notice the text in the bracket, notice that if 2 to the power of m is greater than or equal to n and less than 2 to the power of m plus 1, as it should be from our example and the generalized case formula here, the remainder L, which is n minus 2 to the power of m, satisfies L is greater than or equal to 0 and less than 2 to the power of m, by the fact that L being a remainder, right? So this is the key thing. L is always greater than or equal to 0, less than 2 to the power of m. So now to the proof part. As in the past, we use induction, but this time the induction is on m, and when m equals 0, we must have L equals 0. Reason being, due to the limitation is L is less than 2 to the power of m, in this case 2 to the power of 0, so it should be less than 1. Only natural number less than 1 is 0. I wouldn't say natural number, but positive integer, or just the integer is 0. So L should be 0. Thus, moving on to the next page, thus the basis of 1.9 reduces to J1 equal to 1. Let me rewrite the formula here just so we can clearly see what the formula we're trying to prove. If if number n input can be rewritten in a fashion of 2 to the power of m plus l, and we put that as j of Josephus input, then that turns out to be 2 times the leftover plus 1, the number within that group. Okay, so the basic case is true. Now that we have to look at and evaluate the inductance step. The text says it has 2 parts depending on whether L is even or odd. So let's see. If m is greater than 0 and 2 to the power of m plus L is equal to 2n, even number, then L is even. That's because it's pretty self-explanatory. L is even because if you move over 2 to the power of m to 2n side, it's going to be 2n minus 2 to the power of m. Again, this can be reorganized, factored into 2 times n minus 2 to the power of m minus 1. In this case, we're not worried about the power being negative because the basis case is already considered, and we are considering the case where m is equal to or greater than 1. So there's no chance that it's going to be going to fraction by having negative power here. So that being cleared, L is even, and j2 to the power of m plus L equal to 2j 2m minus 1 plus L over 2. The reason being that this is written this way is, let's see. Okay, so we are going back to the case where the even number is how even Josephus input is outputted. If you look at this text here, 2 to the j2n equal to 2jn minus 1. So we are going to input that. So since 2m to the power of m plus L is even, can be rewritten as 2j 2m minus 1 plus L over 2 minus 1, because we're dividing all the input n by 2, and which is then it's equal to 2 times 2L over 2 plus 1. The reason we can write this way is because by induction, we assume that when m is less than or certain number, m is less than, when number is less than m, then the equality holds, this equality. So we can rewrite it as 2, what's left over is L over 2 plus 1. Again, we rearrange it, then it is now 2 times L plus 1, proving our theorem, not theorem, but the formula above there. So by 1.8, the induction hypothesis, this is exactly what we want, exactly. And similar proof works in the odd case when 2 to the power of m plus L is equal to 2n plus 1. We might also note that 1.8 implies the relation j2n plus 1 minus j2n is equal to 2. Either way, the induction is complete and 1.9 is established. Yeah, we can go on to get to the odd solution. But for the sake of this, reading this textbook, it's not super important. We can dive in the next video how it's derived, and there will be also interesting topic to concept we can explore. Not super hard because we already dealt even number case, right? So Yeah, and once we figure out this solution, we can figure out how to compute really big inputs and compute the Josephus problem for big inputs like 100. So in our case, given that this formula is proven true, J100 can be what? 2 to the power of to the power of, well, 2 to the power of 5 is 32, 6 is 64. So to the power of 6 plus 64 plus 36 is equal to 100. And that leaves us here as 2 times 36 plus 1, so giving us the answer to 73. So the Josephus of 100 is 73, as it should be, given in the textbook here. Okay, so that's it. And for the next paragraph and some of the other new concepts that will be unpacked here, let's